Hey, this is Jack, and this is Lab 5, Magnetic Braking with Faraday. So the overview, introduction, glow script model, and discussion. So the purpose of this lab was to observe and apply Faraday's law in experiment and simulation. And the main results from this lab were that the experimental time was 1.12 seconds and the computational time was 0.974 seconds. So the main concepts and equations were Faraday's law, magnetic force, Newton's third law, Ohm's law, Biot-Savart law, the time derivative of the magnetic flux equation. The model we used was the magnet and aluminum foil, and these modeled a magnetic dipole and a conductive tube respectively. The assumptions were that the only forces acting in the simulation were the magnet were the force of gravity and the force from the loop. And the procedure we used was using a magnetometer on the phone to find the North Pole, recording metrics such as mass of the magnet, width of foil, and a radius and length of the tube, and using a camera to record in time as I dropped the magnet 5 times. On the left are my actual experimental results with trials and times, and on the right are the metrics of the dimensions of what tools that we were using as an apparatus. So right here is my overall glow script code. More on the left side is just general values, standard values that we're using. Center area is more of the functions being defined, and on the right side is pulling it all together and actually simulating it. So right here is the glow script model. On the right side is the actual simulation of the magnet falling through. On the right side is a velocity versus time graph, and as you can see, it's accelerating down with gravity, hits kind of a plateau with just gravity and the magnetic force canceling out with a constant velocity, and then gravity becomes overwhelming at the end again. And again, the time in the tube was 0.974 seconds. So the glow script model questions are: the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing through in opposite directions. Which color corresponds to clockwise current as viewed from above, and which counterclockwise? How can you know? So I said the red current corresponds to the counterclockwise and blue current clockwise, and we know this from Lenz's law. The second question is, what happens to the dynamics of the system when you flip the magnet around? Well, everything generally stays the same, such as the time it takes to fall, the magnetic force. Essentially, it's the same exact situation, only the direction of the current changes. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? I said the experimental time took longer than the computed time, and I think that splitting the tube into more rings or reevaluating the magnetic dipole from Lab 3 could very much increase the accuracy of a computational model. And the fourth question is, what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? And it tells us essentially that there's at the very beginning an overwhelming gravitational force, which is then canceled out during the duration of the tube with the magnetic force, resulting in a constant velocity. And then by the end, also, when it goes out of the tube, having again an overwhelming gravitational force. So the main results that we had were that using the magnetic dipole found in Lab 3, our simulation predicted that it would take 0.974 seconds for it to fall through the tube. In our actual experiment, we found that it took an average of 1.12 seconds. Some sources of error that could very well have influenced this were that we didn't account for air resistance. We didn't account for any friction that might have happened between the tube and the magnet when falling. And there could very well have been an error in calculation from the magnetic dipole calculated in Lab 3. So the discussion what if questions are: what if the resistivity of the conductor was reduced as close as possible to zero? How would the dynamics of the falling magnet change? I said it would cause a larger current, which would result in a larger magnetic force, which would cause the magnet to slow down a lot more when falling through the tube. And question 2 for what if is, what if the holes or slots were cut into the tube? How would this affect the ring current in your model? I said the holes would disrupt the rings, which would reduce the induced current, reduce the overall magnetic force from the loop, and this would result in gravity having a more overwhelming force, causing the magnet to essentially fall through a lot more fast.